All right, so now we're going to start talking about the next geometric figure that we're going to construct with our triangles, and those are angle bisectors, right? So we want to be able to use angle bisectors to solve some problems as well. So before we can do that, we got to remember a couple of things. Number one, we remember what an angle bisector is, and that's a ray that divides an angle into two congruent adjacent angles. So we need to remember that as soon as we know something is an angle bisector, that means it's cutting an angle in half. Right? And so we also want to remember that when we want to measure a distance, we want to measure the shortest distance, right? So anytime we're talking about measuring a distance from a point to a line, it always needs to be at a perpendicular, right? So we're going to stay at that point and go directly at the lines that we're forming a perpendicular segment, right? We talked about that before. All right, so angle bisectors. What we know about angle bisectors, there's a theorem that helps us set up some problems to solve and find some lengths, right? And of course, it's called the angle bisector theorem. And the angle bisector theorem says if, right? If a point is on the bisector of an angle. And again, we got to make a big deal about the hypothesis of these theorems, right? So what it's saying is we have to know that x is sitting on the angle bisector first, right? So either we need to be told that or we need to have the diagram marked, something like that, where we know that this ray is going through an angle and it's creating two congruent angles. If we know that, then what the theorem says is that that point is equidistant to the sides. Right? So if we know that x is already on the angle bisector, then we know that x is equidistant to the sides. And so we have to understand that we're going to measure that distance with those two black segments there so that the segment's perpendicular to the sides. And we got to make sure that those segments are the same length. That's if we're using the theorem. So if the point is already on the angle bisector, then we know it's equidistant. Versus the converse, which says the opposite, right? Which says that if a point is equidistant to two sides of an angle, then it sits on the angle bisector. So we have to know that this point is on, that point is equidistant to the two sides of an angle. And so we're going to know that by showing that a segment going from the point to the side that's perpendicular, because that's how we're going to measure the distance, is the same for both of them. And so we're going to make sure that those two segments are congruent. If that's the case, then we know that x is on the angle bisector. And using the converse to the angle bisector theorem, we're going to use that sort of approach to construct our angle bisectors in just a minute. Okay? All right. So just using this. First example here, we want to find the measure of angle HFJ. Right? Well, angle HFJ is this angle right here. And some things that we want to make sure that we think about and that we check, right? First of all, this point J is sitting on the angle bisector. We know that FJ, ray FJ, is an angle bisector because that point J is equidistant to the two sides. So the converse, by the converse of the angle bisector theorem, right? We know that J is sitting on the angle bisector. It's equidistant from the sides, and we know that because those two segments are the same length, and we're using those segments to measure the perpendicular distance. Since that's the case, the measure of angle HFJ has to be 40 degrees because that bigger angle HFG is being cut in half. And we already know that 1/2 is 40. Okay? So we have to just recognize the fact that J is on the angle bisector, and that's how. The two segments JG, JH are the same, and those are perpendicular segments to represent the distance to those sides. Okay? All right. Next question. What value of x allows point P to be on the angle bisector? right? Well, again, by the converse, that's what theorem we're using. We're going to use the converse of the angle bisector theorem, which says that if that point is equidistant to the sides, right? So we know we're measuring distance because those segments are the perpendicular. And if those distances are the same, then P is on the angle bisector. So what we're really asking is, what value of X will make these two guys the same? We'll set them equal to each other. And X ends up being 7, right? So now we know that P is on the angle bisector. Another question for you. Next example, right? Is there enough information to conclude that ray QS, this should be ray QS, bisects angle PQR? Okay? Well, again, that would require S to be on the angle bisector. And by the converse of the angle bisector theorem, we would have to know that S is equidistant to the two sides. And we want to make sure that we're measuring the distance the same way to both sides. And that means it needs to be at a perpendicular. Well, that's the problem. We don't know that segment SP and SR are perpendicular to the sides. So we're not sure that we're actually measuring the shortest distance from a point to a side, even though those two segments are the same, right? So we cannot say that QS is an angle bisector. All right? All right? Now, some more of what we know about angle bisectors. There's a theorem that talks about the concurrency of an angle bisector. The theorem basically says that if you construct angle bisectors of a triangle, they're going to intersect at a point, and they're going to intersect at a point that is equidistant from the sides. Okay? Well, that makes sense. If you actually go through and look at this, that makes sense. Here's a triangle ABC, that we have angle bisectors constructed. And we know that because these sets of angles are all congruent. And because of that, we know that P is equidistant to each side of the angle. So that means that this segment and this segment are congruent. Well, if you think about going from angle B, bisecting angle B, that means P is going to be equidistant. So PD and PE are going to be congruent. And so now all of those distances are the same. And so P is equidistant to the sides, right? And they're also concurrent, right? Angle bisectors are concurrent. They're going to intersect at the same point. That point is called the incenter, right? That point is called the incenter because if you were to place your needle of your compass at this point, open that up to where the pencil is sitting on one of the sides, if you measure the side from that center point P to side at point D, and draw a circle, then this circle will hit all three sides. It has to, because E and F are the same distance from P that D is, and that's what circles do. They give us a bunch of points that are all equidistant to that center point, right? So it's an incenter. An incenter helps you inscribe a circle, okay? The incenter, therefore, will always lie inside the triangle, versus perpendicular bisector, which gives you a circumcenter, and what that means, right? And because of that, like I said before, PD, PE, and PF are all going to be the same length. Okay, so you get your circle there, and there you go. One last thing that you want to recognize and understand that you can use to help you find lengths, when lengths represent distances, and sometimes that helps us in some real-world situations, right? Here's the diagram of triangle ABC. We're told that P is the incenter, right, which means that it's the center of an inscribed circle, the circle that will hit just the sides inside the triangle. But that's because PD, PE, and PF are all going to be the same length, right? Well, we know that FC is 12 and CP is 13, and that's been labeled in our picture, and we want to find EP. Well, since finding FP, DP is the same thing as finding EP, as long as we can find one of those, we're in good shape. Well, here we have the length of this segment, the length of this segment, and we know that if we find this segment, then it's going to help us find EP, right? Well, if you look, I just highlighted a right triangle, right? So now we have to remember what we use to help find sides of a right triangle. And not the first time you've seen this, but the Pythagorean theorem. That's the theorem that governs the side lengths of a right triangle, which says that leg squared plus leg squared has to equal the hypotenuse squared. Well, in that particular right triangle, the hypotenuse is 13, so we're going to square 13. That means that FC is a leg, so it's going to be 12 squared. And we're trying to find that other leg. Oh, so we're not going to cube the x, we're going to square it. And there's your equation. So x squared plus 144 equals 169. Subtract the 144, you get 25, and then square root both sides, and x ends up being, in algebra world, plus or minus 5, but since this represents the length of a segment, we can't use the negative. So x is 5. Since x is 5, that means that EP is going to be 5 as well, right? So just, again, wanted to show you so that you can maybe recognize the fact that you can use Pythagorean theorem because these are all right triangles. These are small right triangles drawn in this bigger triangle. Okay? So, starting to introduce a lot of vocabulary terms. Some of them are going to sound a lot alike, right? The point of concurrency for angle bisectors is a lot like the point of concurrency for perpendicular bisectors, but there are some differences as well, right? So, we want to remember, try to find some way to remember the similarities and the differences to an incenter and a circumcenter, right? So a Venn diagram helps. On the outside of those two circles are going to be what's different about incenters and circumcenters. And it's not in your notes, but if you take these notes down, it might help you kind of keep track of whether you're talking about an incenter or a circumcenter, right? And what are some of the differences? Right, the first difference between the two is that this guy is always inside the triangle, the incenter is, right? Where the circumcenter could be inside, could be outside, or could be on the triangle, right? Depending on what type of triangle it is. We learned that from last time. What else is different? What else is different? Well, incenter is equidistant to what? To sides, right, of a triangle. Whereas the circumcenter is equidistant to the vertices or the angles, right? Let's see, what else is different? The incenter, what? Is used to inscribe a circle, whereas this is used to circumscribe. A triangle, right? Okay. Also, you have to remember that an incenter is created by angle bisectors, where the circumcenter is created by perpendicular bisectors, right? So one of them is created by bisecting angles, the other one's created by bisecting segments. The only similarity between the two is that both of them are those points of concurrency, right? They're both created by segments that are intersecting all together. Okay? Maybe that'll help. So angle bisectors lead to incenters. Perpendicular bisectors lead to circumcenters. Okay? All right. Now it's time for some constructions. I think I found a way to show you in a video how to do this. So let me try something here. The angle bisectors are a little weird. Sorry. I'm going to pause the video just for a second and try to get this fixed. Okay, I think I got it. And we're going to go back to your mid-segment notes, right? That's where we found angle bisector the first time. So if you want to stop the video right now, go grab those notes and then find the angle bisector that we skipped before, okay? Okay, so hopefully you have those now, and we can use that so that your homework can be used for practice, right? Now there are steps there that you can use to help you figure out how to draw these as well. But let's try something here. There we go. Now I'm good. Sorry. All right. So I'm going to bring up my compass here. And so here's the thing. All right. So it looks like I'm not going to be able to get this done right now. Sorry about that. We'll go ahead and stop the notes here. And if you missed and you need to know how to construct an angle bisector, go ahead and come in during STAR, and we'll sit down and go over it. Okay? Homework for your worksheet is out in Canvas. This you should be doing the angle bisector page in your construction packet, right? Both sides, front and back. All right? And then we'll see you next time.